Hello, I'm doing a video on organic chemistry, A2 organic chemistry. So I'm not going to discuss AS content in here. Everything on AS will be in my other video. So I'm dividing this video in three sections. First, I'm going to talk about benzene, its structure, its reactions. Then I'm going to talk about all the other functional groups we have in our A2 syllabus. And at the end, we're just going to talk about the two new mechanisms added to the syllabus. One mechanism has been added, addition elimination, and there's electrophilic substitution, which is part of A2. All the other four mechanisms are in my other video. Okay, so let's begin. I'm gonna add timestamps so you can skip to them if you want. It's gonna be in the description. So let's start with benzene or arene. We need to know about the structure of benzene. These are marking points taken from ON20 variant 4 to question number 7. It's a regular hexagon or planar. All carbon-carbon bonds have the same length. All of the bond angles are 120 degrees. All carbons are sp2 hybridized. And the carbon-hydrogen bonds are s-sp2 overlapped. The s orbital is from hydrogen and the sp2 orbital is from carbon. Okay, it's a sigma bond. The C-C bonds have sp2 overlapping. It's a sigma bond as well. And there's also overlapping between the p orbitals of the carbons, right? We get another C-C bond, which is the pi bond. This is the structure of benzene, right? Something like this. Here we go. Here we go. And there's resonance between them, right? It constantly switches from one to the other. These are resonance structures. Okay, so the C-C bonds have both sigma and pi bonds. The sigma bonds are between sp2 orbitals and the pi bonds are between p orbitals. Only hybrid orbitals cannot form pi bonds, by the way. They can only form sigma bonds. Only p orbitals can form pi bonds. Okay, so pi bonds are formed due to overlapping. These last 3 points are from another mark scheme, a bit older. Pi bonds are formed due to overlapping of p orbitals. This is basically the same point, right? And pi electrons are present above and below the ring, and the electrons are delocalized. Okay, so let's learn about the nomenclature. This is the structure of benzene on the right. So let's learn about the nomenclature of monosubstituted benzene. This first one, C6H6, that's benzene. Then we have nitrobenzene. The nitro group, it doesn't matter. In a monosubstituted compound, it doesn't matter where the group is attached. It's going to have the same name and it's going to be the same compound. So we have nitrobenzene, and if NH2, if an amine is attached to the benzene ring, it's called aniline or aminobenzene, phenylamine basically. If OH is attached, it is called phenol. If CH2OH is attached, it's benzyl alcohol. It's an aliphatic alcohol. If a halogen is attached, it's called chlorobenzene or bromobenzene. If an alkyl group is attached, for example, if a methyl group is attached, it's called methylbenzene or toluene. And aldehydes and carboxy acids can be attached as well. And if a carboxylic acid is attached to the benzene ring, it's called benzoic acid. So what are the characteristic reactions of benzene ring? It's electrophilic substitution. I've described this at the end. So one question before we start this, we need to know the differences between benzene and the intermediate formed during electrophilic substitution. This is also a common question. You'll find this in the specimen paper for 2022. The intermediate actually has the pi system, which extends over 5 carbons, okay? But in benzene, it extends over 6. There are only 4 pi electrons in the intermediate, while there are 6 pi electrons in benzene. One carbon is sp3 hybridized in the intermediate, but all carbon atoms are sp2 hybridized, right? In benzene. All the other ones in the intermediate are sp2 hybridized except that this special one, this carbon over here, okay? And one carbon has a bond angle of 109.5 degrees in I, the intermediate, which is tetrahedral, the one I've circled, okay? So what are the reactions of benzene? All of these are electrophilic substitution reactions. First, we're going to start with nitration. The reagents are concentrated nitric acid, concentrated H2SO4. You need to mention concentrated, and the temperature is 25 to 60 degrees Celsius according to the syllabus. This is the new temperature. You can go with 55, it's okay. So you need to know how the electrophile is formed. There are multiple equations, but I would recommend learning this. This is the best one. We get the nitronium ion, which is the electrophile. Electrophiles are positive in nature. They love negative things, negative electrons, okay? So this is the mechanism. Make sure you draw the you need to draw curly arrows, and it needs to be drawn from the nucleophile to the electrophile. Although the electrophile is attacking the benzene ring, the arrow will always be from the nucleophile to electrophile. So in the first step, you will draw the arrow from the benzene ring to the electrophile. Then we'll get this intermediate, the one I've discussed above. Uh, and then there's heterolytic fission of this bond. Okay, heterolytic fission occurs and hydrogen actually sacrifices its electron, which fills up the deficiency in the benzene ring, and this is how the H2SO4 is regenerated. So it's actually acting as a catalyst. Next, we're moving on to Friedel-Crafts alkylation. Here, the reagent is an alkyl chloride, and we need anhydrous aluminum chloride catalyst. We do need heat for this. We need to know how the electrophile is formed. CH3Cl plus AlCl3 forms AlCl4 to the power minus 1, and CH3 plus, that's the electrophile. So it's going to attack the benzene ring. The mechanism is the same. We just need to know how AlCl3 is regenerated again, since it has a catalytic role here. Okay, the H plus released actually reacts with the AlCl4 minus to form AlCl3 and HCl. Next, moving on to Friedel-Crafts acylation, we're going to add an acyl group, right? Acyl group, the CH2CO group or CH3CH2CO group to the benzene ring using an acyl chloride and anhydrous AlCl3, and heat is also required. The formation of the electrophile is almost the same, the mechanism is also the same, and the regeneration is the same as well. Rather than getting an alkyl group, we're just getting the CH3CO group. I just use skeletal here. Okay, you could also write this as COCH3, same compound. Okay, moving on to halogenation. We need chlorine and anhydrous LCl3 or bromine and AlBr3. You could also use FeCl3 and FeBr3, they're accepted as well. Their goal, I mean, what is their role? They act as halogen carriers, or they have a catalytic role. The formation of the electrophile is shown over here. Chlorine reacts with the LCl3 to form the Cl plus electrophile. The mechanism is the same, and at the end of the reaction, AlCl3 reforms again by reacting with H plus and AlCl4 minus react to regenerate it. There are two other reactions of benzene. You can oxidize the side chain, okay, using hot concentrated KMnO4 acidified or alkaline KMnO4 followed by acidification. So regardless of the length of the chain, benzoic acid will always be produced. Okay, benzoic acid is the permanent product. Always, you'll always get benzoic acid regardless of the length of the chain. Okay, remember that. Even if it's methyl benzene or ethyl benzene, you're gonna get benzoic acid. What about reduction of benzene ring? This is very important because we get an aliphatic compound from the aromatic one. So we just add hydrogen to the benzene ring, and we need a platinum or nickel catalyst and heat. They also undergo free radical substitution, but just chlorine with UV light does not react with benzene ring. The bonds are too strong. But if we have methyl benzene, the aliphatic part can actually react with chlorine, right, to form this derivative, and HCl will be released. This is free radical substitution. So as we can see, methyl benzene reacts with chlorine in two ways, in two different conditions. If UV light is given, free radical substitution occurs. If we have the AlCl3 catalyst, then electrophilic substitution occurs. Really important, guys. Next, we need to know what orthopara directing groups are and what meta directing groups are. So orthopara directing groups are those which direct to the 2 and 4 position. So remember, the new group that's coming into the benzene ring, there's no priority in that. Like, there's no priority on the group that is coming into the benzene ring. There is always priority. The group that is attached to the benzene ring in the first place gets priority. Okay, remember that. So for example, you were given the data booklet beforehand, right? Now you won't be given the booklet anymore. So you need to memorize 6 groups, okay? All alkyl groups, OH, phenol, aniline, NH2, these are orthopara groups. Why? If they ask you, because they have a electron donating tendency. So they are 2, 4, 6 directing, okay? As you can see in this diagram, the NO2 group will either go to the 2 or 4 position, okay? Remember that. Also, I've made a mistake here, like constantly HN3 and H2SO4 only refers to the alkyl, like methyl benzene. Phenol doesn't require those conditions, okay? It will react at room temperature with HNO3 and H2SO4. What about meta-directing groups? This question was actually there, in fact, in March 2022. If you have NO2, COH, or COR, this does require heat, by the way. Listen, phenol doesn't require heat, but this requires heat with nitration, I mean. So these groups are electron withdrawing in nature because they have so many electronegative atoms, right? So they have a tendency to withdraw electrons, so they are 3, 5 directing. The NO2 group will either go to the 3rd or 5th position. Now we need to know about halogenaries and halogenalkanes, like aryl chlorides and alkyl chlorides. So halogenalkanes are much more reactive than halogenaries. This is because the lone pair on chlorine takes part in the delocalization of the benzene ring. Uh, right. So basically, the halogenoalkane, right? The halogenalkane, it is much more reactive than the halogenarine, mainly because the lone pair of the chlorine takes part in the delocalization of the benzene ring. Okay, so the CX bond in the aryl chloride has a partial double bond characteristic. That's why it's so hard to break. That's why it's much less reactive, the aryl chloride, I mean. For example, C6H5Cl, phenyl chloride, chlorobenzene basically does not form a precipitate with AgNO3 silver nitrate. It does not form the silver chloride white precipitate when we heat it. But the alkyl chloride does produce a white precipitate with AgNO3 at room temperature slowly, and if we heat it, it almost forms the white precipitate immediately, right? Also, we can hydrolyze um, the alkyl chloride using NaOH aqueous plus heat, but we cannot hydrolyze the aryl chloride. Okay, moving on. Alcohols. The only thing from alcohols in the A2 service is esterification. We know that alcohols react with carboxy acids in the presence of concentrated H2SO4 and heat under reflux to form esters. But they also react with acyl chlorides at room temperature to form esters. Okay, remember that. HCl will be given off, white fumes will be seen as a byproduct. Now we are dealing with phenol, which is acidic in nature. So how do we produce phenol? There's no direct way to do it, but we can get nitrobenzene, reduce it to form aniline. Then we can react aniline with HNO2, nitrous acid, or with sodium nitrite and HCl at a temperature less than 10 degrees Celsius. Okay, there has been a change to the syllabus. In the mark scheme, you'll see that it was less than or equal to 10 degrees Celsius beforehand. Now it's just less than 10. So you can opt for 5 degrees Celsius or something. So you're going to get the diazonium salt, which can be warmed with water to form phenol. So actually hydrolysis, right? Hydrolysis of the diazonium salt takes place to form phenol. And we're going to get nitrogen gas. Nitrogen gas is also produced. Okay. So it also phenols now react with, that was production. Phenols react with metals because they're acidic to form salts plus hydrogen gas. So sodium phenoxide is formed. It is also acidic enough to react with bases, right? Like sodium hydroxide to form a salt and water. Alcohols cannot react with bases, okay? But they are not acidic enough to react with carbonates, okay? We can differentiate phenols with carboxy acids, right? By using sodium carbonate. We would see fizzing with the carboxy acid, but not with phenol. So we can also nitrate the phenol, right? We can add the nitric group, but this occurs at room temperature. You don't need concentrated HN3 or concentrated H2SO4. You can just go with dilute, and it occurs at room temperature. If you did use concentrated and heat, what would happen? You would get 2,4,6 trinitrophenol immediately, right? Picric acid, I guess. It's picric acid, yeah. So why though? Basically, this was in Feb March 2022 as well. The p orbital on the oxygen overlaps with the ring, or you could say that the lone pair on oxygen is delocalized into the ring. So think about it. The ring becomes more electron rich, the density increases, right? Now an electrophile is positive. It will like be more likely to attack the benzene ring, right? So it attracts or polarizes electrophiles better. So moving on to bromination. Uh, it reacts with aqueous bromine at room temperature to form 2,4,6 tribromophenol. It's a white precipitate. This is a test for phenols. Phenols can also be used to form azodyes by reacting with diazonium salts, okay, to form azodyes. They are colored compounds, okay. They also react with FeCl3. This isn't in the syllabus anymore, but you should know it, to form a purple solution. This is also a test for phenols, just like the bromine one. And we can also go for ester formation. Phenols react with acyl chlorides at room temperature to form esters and HCl as byproducts, okay. So why is phenol acidic actually? The lone pair on oxygen takes part in the delocalization of the benzene ring, right? So this actually, causes the OH bond to be weakened, and the H plus is lost more easily. This facilitates the loss of H plus. The key word is the OH bond is weakened due to the delocalization, right? Also, think about after losing the H plus, the phenoxide ion is actually stabilized by the electron withdrawing effect of the benzene ring. Okay, as a result, think about it. Since the negative charge is delocalized into the benzene ring, it is stabilized. It will be harder to get the H plus back. That's why it's stronger. So you need to talk about both points, weakening the OH bond as well as the stabilizing of the phenoxide anion. Okay. Right. So if you compare the acidity of phenol, water, and ethanol, phenol is more acidic than water, and water is more acidic than ethanol. Why is that? So I just explained phenol beforehand over here, right? We know why phenol is acidic, but what about ethanol? This is the same explanation. So what about ethanol? Why is ethanol so weak? Why is it weaker than water? Basically, the ethyl group is electron donating. It has positive inductive effect, right? So it actually strengthens the OH bond rather than weakening it. As a result, it is harder to remove the H plus. Also, the CH3CH2O minus, the ethoxide anion is destabilized due to the electron releasing nature of the alkyl groups. Okay, that's why it's such a bad acid. Okay, moving on to carboxylic acids. So in A2, we only need to know the production of benzoic acid. How is this done? I taught you beforehand, by the oxidation of the side chain. Regardless of the length of the chain, using hot concentrated acidified KMNO4, we're gonna get benzoic acid. Okay, what reactions do they undergo? Mainly, they react with PCl5, PCl3, and SOCl3, SOCl2, thionyl chloride to form acyl chlorides, just like alcohols in AS chemistry. So you need to remember these reactions: phosphoryl chloride, phosphorus acid, SO2, and HCl. We need these. Okay, we need to know what products are formed. Like thionyl chloride, this reaction was there in Feb-March 2022. Okay, the last one. Also, we can oxidize a few carboxylic acids. Which ones though? KMNO4 can be used. Okay, so which ones though? Methanoic acid and ethane dioic acid only. These can be further oxidized using hot concentrated acidified KMNO4 plus heat to form carbon dioxide and water. Also, methanoic acid can be oxidized using some other things as well, like Fehling's reagent, Tollens reagent, which is why it gives a positive test with those. And also, potassium dichromate can be used to oxidize methanoic acid. Okay, so if we compare the acidities, the strongest acid is ethanoic acid, followed by phenol, followed by ethanol. So we know about phenol and ethanol, but why is ethanoic acid so much stronger than phenol? Okay, mainly because the OH bond is weakened due to the presence of the electronegative oxygen or the CO double bond. So H plus is easily lost. So H plus is easily lost, right? And the carboxylate anion is stabilized by the electron withdrawing nature of the carbonyl group, okay, or the electron withdrawing nature of the oxygen atom. Okay, so we know this. I've explained this beforehand, why ethanol is weaker and why phenol is acidic in general, right? So we need to know this as well. This is from a recent paper as well, maybe May June 20. Suppose you're given three acids, CH3COH, I mean CH2, CH3, CH2COH, CH3CHClCOH, and CH2Cl, CH2COH. Okay, so who's the most acidic? It's going to be 2-chloropropanoic acid, then 3-chloropropanoic acid, then propanoic acid. So what is the reasoning? In general, the ones with the chlorine atoms are more acidic. Why? 2-chloro and 3-chloropropanoic acid are more acidic because they contain an electronegative chlorine atom, which weakens the OH one more, right, and stabilizes the carboxylate anion. But if we compare 2 and 3, just think about it. In 2, the chlorine is at a closer proximity to the H plus that is lost, right? So it has a greater effect, and it can weaken the OH bond more, and the carboxylate anion is stabilized more. Okay. Moving on to esters, how can we produce them? We know that they can be produced using carboxylic acids and esters from AS, but in A2 we need to know that acyl chlorides can be reacted with alcohols, phenols, right, to produce esters. But this occurs at room temperature, and this is a condensation reaction because a small molecule of HCl is released. We're going to see steamy fumes. Okay, white steaming fumes. Moving on to acyl chlorides. So what about acyl chlorides? By the way, you should know the names of these compounds. If acyl chloride reacts with phenol, we get phenyl ethanoate, and if acyl chloride reacts with um, this, like if both arene groups, arene rings are present, right, we're gonna get phenyl benzoate. This is a really important compound. Okay. So remember that acyl chlorides are basically just stronger carboxylic acids. Carboxylic acids on steroids, right? They can do anything that the carboxylic acid does, but better. Okay. So how do you produce them? I taught you beforehand by using PCl5, PCl3, or SOCl2 with carboxylic acids. By the way, the first one and third one occur at room temperature, but if you want to use PCl3, you will require heat. Okay, you're gonna get phosphorus acid. So they react with PCl5 to get acyl chlorides, right? Now, what reactions do they undergo? They take part in hydrolysis reactions with water. We're going to get carboxylic acids and HCl gas. This occurs at room temperature. By the way, this is the addition elimination reaction mechanism which has been added. I discussed this at the end. Okay, you can skip there if you want. They also take part in ester formation by reacting with alcohols and phenols to form esters. This occurs at room temperature as well. They also form amides, by the way, by reacting with amines and ammonia. This also occurs at room temperature. By the way, you cannot use carboxylic acids to form amides. You are only allowed to use acyl chlorides. Remember that. Okay. Now, what about the hydrolysis? This is from Major 21, variant 42. Let's compare the hydrolysis of acyl chlorides, alkyl chlorides, and aryl chlorides. There was also a table in Major 17.4.2. I've taken some information from that as well. Basically, acyl chlorides are the best, easily hydrolyzed, then alkyl chlorides, then aryl chlorides, which cannot be hydrolyzed at all. So in acyl chlorides, the CCl bond is more electron deficient since it is also attached to an oxygen atom, or the CCl bond is weakened since it is also attached to oxygen. So it's really easy to break. In aryl chlorides, the CCl bond is part of the delocalized system, or the partially, it has a partial double bond character, right? Or the partial double bond character of the CCl bond. There's some wrong wording here. There's a partial double bond character of the CCl bond, right? So it is stronger. Okay, this is from the Mark scheme, but there's wrong wording. Also, you could say that the p orbital on the chlorine atom actually delocalizes with the pi ring of the benzene ring, right? So it has a partial double bond characteristic and it's really hard to break. It requires a lot of energy. And alkyl chlorides like like ethyl chloride, it is strengthened by the electron donating effect of alkyl groups, right? So it can be hydrolyzed, but it's harder to break compared to acyl chlorides, because in acyl chlorides we had an electron withdrawing tendency, so it was weakened. But here it's strengthened, but it can still be broken. For example, if you apply cold silver nitrate, we're going to get a white precipitate with acyl chlorides and alkyl chlorides, but it forms immediately with acyl chlorides, but it takes some time with alkyl chlorides. Aryl chlorides do not form a white precipitate. And if you use hot silver nitrate with HNO3, aryl chlorides still produce no precipitate. That means the bond cannot be broken, and both alkyl and acyl chlorides form the white precipitate almost immediately. Moving on to amines. So amines can be produced mainly, this is a reaction from AS chemistry of halogen alkenes. They can be reacted with ammonia or amines, ethanolic ammonia or amines, in the presence of heat in a seal tube or heat under pressure to form amines. Okay, so we can use ammonia and react them with halogen alkenes to form amines. We're getting a primary amine, or another primary amine can react with a halogen alkane to form secondary amine, right? So if you think about it, this is present in the reaction mixture, right? So if it is heated in a sealed vessel, the reaction continues and further steps occur. So this one can act as a nucleophile because the lone pair of nitrogen can be donated. We've seen this in February 2022, variant 42. So it further reacts with the halogen alkane left in the container to give more derivatives, and we get a secondary amine. The reaction continues till all hydrogens are used up. Also, we can get amines by reducing nitriles using lithium aluminum hydride or hydrogen plus nickel, or we could reduce amides using lithium aluminum hydride only, okay, to get amines. What reactions do they undergo? They can form amides by condensation reactions with acyl chlorides at room temperature, both ammonia and primary amines, also secondary. Now let's move on to aniline. This is phenylamine. How can we produce it? There's no direct way to do it from benzene. We can form nitrobenzene first, then reduce nitrobenzene using hot tin and concentrated HCl to get aniline. What reactions do they undergo? Just like phenol, you can perform bromination of aniline to get a white precipitate at room temperature. You can also form diazonium salts by reacting with nitrous acid or sodium nitrite plus HCl at a temperature less than 10 degrees to get diazonium salt. Now the diazonium salt has two routes. Either you can form the azodie or you can form phenol. Okay, so if you warm the diazonium salt with water, you're gonna get phenol and nitrogen gas. Okay, and if you react it with phenol in the presence of sodium hydroxide aqueous, it's going to form the azodie. So remember this, the azodie, the triple bond breaks, it forms a double bond. The nitrogen will always bond to the carbon opposite to the phenol's carbon. Okay, remember that, unless you're guided to something else. If you're not guided, you need to remember this. The azodie will form a bond at the carbon opposite to the OH. Okay, remember that. So comparison of basicities of ethylamine, ammonia, and aniline. Ethylamine is the strongest base because the ethyl group is electron donating, positive inductive effect. So the lone pair on the nitrogen is more available to accept protons. So remember that the more available the lone pair is, the stronger the base you will have. Okay. And on the other hand, the lone pair on nitrogen is delocalized into the benzene ring, right? That is why it is less available in phenylamine. Moving on to amides. Amides can be formed by reacting acyl chlorides with ammonia, primary amines, aniline. We are getting amides that way. This occurs at room temperature, but you cannot use carboxylic acids. Remember that, okay? What reactions do amides undergo? They take part in two reactions mainly. Mainly hydrolysis. You can perform acidic or alkaline hydrolysis. If you perform acidic hydrolysis, you're going to get an acid and salt. If you perform alkaline hydrolysis, you're going to get a salt and amine. I'm going to talk about the hydrolysis of esters as well. Acidic hydrolysis leads to carboxy acid plus alcohol. Alkaline hydrolysis leads to salt plus alcohol, okay? Because the carboxylic acid reacts with the base to form a salt. Now, I didn't talk about polymers in details, condensation polymers, but do remember this. Polyesters can be formed by reacting diols with either dicarboxylic acids or diol chlorides, acyl chlorides basically, or you can use a hydroxycarboxylic acid, something that has both an OH and a COH group. That way, you don't need two monomers to form a repeat unit. But in this upper one, you need two monomers to form a repeat unit. The same goes for amides. You can use diamines and dicarboxylic acids or diol chlorides, or aminocarboxylic acids, namely amino acids. What is an amino acid? It basically has a carbon, a hydrogen attached, a variable R group, a carboxylic acid group, and an amine group. So if you line them up side by side, they can form polymers, okay, by condensation reactions. So there are 20 amino acids. You will be given information if you want. If you're asked to answer, okay, because the data booklet isn't given anymore, so you don't know the side chains. Also remember this, if you're asked to draw a dipeptide or tripeptide, remember for a tripeptide there will be two peptide bonds, for a dipeptide there will be one peptide bond, and you cannot draw dangling bonds in that case. But if you're asked to draw a repeat unit, you can draw those dangling bonds. So I have some extra things for you. This is bonus. These are from some previous years. Remember that I taught you hot acidified KMNO4 can break down ethanoic acid and methanoic acid, and obviously ethanol can be oxidized to form ethanoic acid. Alkaline iodine aqueous. This is the iodoform test. So typically ethanol, all methyl ketones, and some secondary alcohols can give this iodoform test positive result. I've discussed this in the AS video. Why ethanol though? Thing is, even though ethanol is an aldehyde, check this out. Even though it's an aldehyde, it has the methyl ketone group, right? That's why it can give a positive test. But the others don't. What about this one, propanone, it has a methyl ketone group, right? That's why it gives a positive test. What about tolerance reagent? All aldehydes. This is the test for all aldehydes and one special carboxylic acid, which is methanoic acid. Why though? Check this out. This is methanoic acid, HCOOH. Even though it has a carboxylic acid group, it also has the CHO group, so it can be further oxidized to form carbon dioxide and water. So 2,4-DNPH is for all ketones and all aldehydes. We get an orange PPT. Okay, orange PPT. Phalings and toluenes are for all aldehydes. Phalings, red PPT, toluenes, silver mirror, and for one special acid, which is methanoic acid. Moving on, hot KMNO4. It can oxidize all primary and secondary alcohols to aldehydes and ketones respectively, all aldehydes to carboxylic acids, oxidative cleavage of alkenes to form carbon dioxide, water, ketones, or carboxylic acids, and two special acids, namely methanoic acid and ethanediol acid. The iodoform test is positive for four of these groups: ethanol, ethanal, all methyl ketones like propanone, and secondary alcohols with the CH3 group. Okay, now you also need this. NABH4 can only reduce aldehydes and ketones. So LILH4 is just NABH4 on steroids. Okay, so LILH4 can reduce aldehydes, ketones as well, and extra nitriles to form amines, amides to form amines, and carboxylic acids to form alcohols, primary alcohols. Okay, so hydrogen and nickel can reduce alkenes, benzene to form cycloalkanes, and nitriles to form amines. Okay, remember this. Oxidative cleavage can only occur using hot concentrated K1O4. If you use cold dilute, you're gonna get diols, and yeah, that's it. You cannot use dichromate to do that. So check this. How would you differentiate between these compounds? Something that reacts with only methanoic acid here, it's going to be toluenes or phalings. We would get a silver mirror or red precipitate accordingly. How could we differentiate this ketone from the others? By using 2,4-DNPH or aqueous alkaline iodine. We would get a yellow PPT for aqueous iodine and orange PPT for 2,4-DNPH. What about ethanediol acid and methanoic acid? Something that reacts with both of them but not the one in the middle. We needed hot concentrated acidified KMNO4. It would decolorize the solution and bubbling would occur. Okay, so these are just some reactions that occur at room temperature and require heat under reflux and just require heat. Okay, this is mainly these are mainly the AS reactions. The A2 ones aren't included here, but remember in A2 most of them, the acyl chloride reactions, they occur at room temperature. Only Friedel-Crafts alkylation and acylation. Okay, Friedel-Crafts alkylation and acylation require heat, and you know nitration of benzene requires 55 degrees Celsius. So we don't need many conditions in A2. We need to know that for diazonium salt production we need a temperature less than 10 degrees, and for reduction of nitrobenzene we need heat, hot tin plus concentrated HCl. But you can learn these if you want. This is mainly for AS chemistry. At room temperature, we have the reaction of 2,4-DNPH, condensation reaction, decolorization of bromine, test for unsaturation, PCl5 and SOCl2, reaction of sodium with alcohols, phenols, carboxylic acids, cold dilute KMNO4, right? The iodoform test, then any HX with alkenes, and the other ones require heat and heat under reflux. Okay, so heat under reflux is mainly for this is mainly for esterification and oxidation of alcohols and aldehydes. Okay, the other ones do not require heat under reflux that much. Some nucleophilic substitution reactions of alcohols require heat under reflux as well. Like if you want to react HX HCl with CH3CH2H, you can say heat under reflux. No problem if you don't. Okay, so let's go to the last part of the video. So here I talked about the mechanisms, the two that are in the syllabus: electrophilic substitution and addition elimination. The other four, right? Free radical substitution, electrophilic addition, nucleophilic substitution, and nucleophilic addition are in my other video at the end of AS Organic Chem. So here I've shown you electrophilic substitution already. The arrow needs to be curly and it needs to be drawn from the nucleophile to electrophile. So I'm showing the nitration of the benzene ring here. First step, arrow from the benzene ring to the nucleophile, I mean to the electrophile, right? Then we have this hybrid compound with one sp3 hybridized carbon. The ring has to cover 5 carbons, by the way. Okay, remember that. If you draw a ring like this, you won't get marks. Then there's heterolytic fission of the bond. So the electron fills up the deficiency of the ring, and we get a nitrobenzene, and H plus is released. And this is the new addition to the syllabus. This is addition elimination of acyl chlorides. I've shown you 2 reactions here. One of them is hydrolysis of acyl chlorides to form carboxylic acids. This is taken right out of the course book. So water is acting as the nucleophile. The carbonyl is the carbon is electropositive, right? Because the oxygen pulls the electron towards it, the cloud towards it. So at first the nucleophile attacks the electropositive carbon, and since carbon can't have 5 bonds, that's why this bond breaks over here, right? So this is the hybrid compound that we get. In the hybrid compound, what actually happens? Heterolytic fission of this bond occurs. So chloride is released, and this double bond is reformed again. So a pi bond is broken and formed again. And a sigma bond was formed initially. This sigma bond was formed initially, and this sigma bond is being broken here. But think about it. If this bond reforms, this carbon will have, like, it won't have 5 bonds anymore. Why? Because since this reforms and this breaks down, we solve the bond problem. But what about this? We need to fill up this deficiency over here, right? This one over here. So mainly, why is this deficiency present? This oxygen over here, this gave one of its electrons to this carbon, which lost an electron due to this oxygen over here. So it has a deficiency of electrons. This is filled up by heterolytic fission of this bond, this OH bond. So we actually end up with an H plus and Cl minus released, which react together to form an HCl byproduct, and we get the carboxylic acid. So this was actually added in the March of 2022 paper. This is from question number 6C from that paper. This is the mechanism. So you need to show the lone pair on nitrogen. It is attacking the acyl chloride, the electropositive carbon. You need to show the dipole and the breaking of the pi bond, okay, the C-double-O bond. Then in this next step, you need to show heterolytic fission of the CCl bond, and you need to show that the double bond reforms again. But you know what? They didn't show how this positive deficiency was filled up. If you want to know how this actually happened, this was the compound, right? So basically, heterolytic fission occurred, and we filled up that deficiency. Okay, that's what happened, but they did not show it in the mark scheme, and at the end we get that product on the right hand side. Okay, so you can check this out, and that's more or less it. So if you have any other questions, you can ask me, and I'm going to link the video for AS Organic Chem over here. You can watch that if you want. Okay, later.